So we're going to use the upper rectangles now. So we're going to do the same sort of thing. So I'm going to form rectangles, but this time I'm going to go up to the instead of the upper left corner of the rectangular strip being matching with the function, I'm going the upper right corner. So the upper right corner of this rectangular strip is going to match with the function here. So this is now the upper rectangle. There's for L1. The same width occurs. Then I go to the upper rectangle for the second rectangular strip, and I'm now forming L2 for that rectangle. That's L2. Then I go to this upper rectangle here, form this upper rectangle, because the upper right corner of each rectangular strip is touching the function. So this is L3. And then I do the last upper rectangle, which goes all the way up here. Which is this entire strip here, and that's length 4. Okay, and all the W's, the widths are still the same. Okay, so what we're going to do now is we're going to do exactly the same thing. So I've got the function. So now instead of doing the lower rectangles, I'm going to do the upper rectangles. So the upper rectangles is again width times length 1 plus width times length 2 plus width times length 3 plus width times length 4. Now the lengths of each of these rectangular strips is the function on the right side of the strip. Okay, so now it's going to be again w times x squared plus 1, but I'm just going to put in the values now. So you've seen this done once. So the width is a half. Then we've got x squared plus 1 as the function. But now this time it's where x is 1/2 right off the bat. So it's 1/2 squared plus 1 plus then a half times 1/2, sorry, not 1/2, now it's going to be 1, because the x value for the second strip, for L2, the x value is 1. And the y value is 1 squared plus 1. So this is L2 here. Then I've got the same width of a half. And then this is for length 3. So the rectangle, the upper rectangle here is the y value. The length of this is y value of this function when x equals 3/2. So that's 3/2 squared plus 1. And then for the last rectangle, it's again a half rectangular strip, and this time it's going to be when x is 2 all the way up to the function. So it's going to be 2 squared plus 1. Okay, and then the same sort of thing, we've got a half times a half squared is a quarter plus 1 is 5/4 plus a half multiplied by, there's 2 again, plus a half. Here is 9/4 plus 1, so that's 13/4 plus a half times, well, 2 squared is 4 plus 1 is 5, so that would be 5 here. Okay, and then when we continue that, we end up getting a value of 5.75 units squared for the upper rectangles, the area of the upper rectangles. So again, we're going to see now that this area of the upper rectangles is now going to be greater than the area under the curve because of all the overlap. These rectangles are now all above the curve. So it would be intuitive to see that the actual area under the curve is somewhere between 5.75 units squared and 3.75 units squared. Now we could maybe take an average of that. But that wouldn't be the most accurate. But what we can say though is that the lower area, the lower rectangles, that area is less than the actual area under the curve, which is less than the area of the upper rectangles. Okay, so that's one thing that we can say. Now, what could we do to make this a little bit more accurate? How could we, because this is, there's a difference of 2 units squared between those two estimates. What might we be able to do in order to make the estimate much closer to the actual area under the curve? So what we could do, if you haven't thought of it, which I'm sure you have though, is we could probably take this function, and instead of breaking it up into 4 rectangular strips, what about cutting these in half themselves and then setting up, I'm not drawing the whole rectangles, but setting up now 8 rectangular strips. We would again have lower rectangles and upper rectangles as we go, but we notice here that for this first one that I just drew here, there's very little empty space there. Okay, there's a little bit more there, a little bit more there, but the first one there's very, very little. So obviously as the curve gets steeper, we see there would be more and more empty space. Or, so that's like 8 subintervals. What if we were to split those in half again? So instead of 8, we would have 16 subintervals. Okay, so you see where this is going. Between each of these subintervals, the tops of the subintervals, the rectangular strips, and the function, we see that there's less and less space that would be formed there. So there's an area finder on the CD of our textbook that has been able to set up a few calculations for us quickly. So if we were to look at the different values of the upper rectangles and lower rectangles, if we had 4 rectangles, from what we had before, we had 3.75 for the lower, the area of the lower rectangles, 5.75 is the upper area, and the average then was 4.75. If we went to 8 subintervals, 8 rectangular strips, the lower area would be 4.1875. Sorry, 75. And the upper area is 5.1875. And then the average of those is 4.6875. If we then jumped up to say 20 subintervals, and we say we'd have 20 rectangular strips, the area of the lower rectangles is 4.47 units squared, and the area of the upper rectangles was 4.87 units squared, and the average was 4.67 units squared. And then if we jumped up more to 50, so obviously if we were to do, we could probably calculate 8 and it wouldn't take us a whole lot of time. If we calculate the area, upper and lower areas of 20 rectangular strips, that would take us a much longer time, and then even 50 even longer. So that's why we use let technology do that for us. So the area of those lower rectangles when there were 50 subintervals would be 4.5872, and the area of the upper rectangles was 4.7472, and the average of those was 4.6672. So we can sort of start to see that the average is starting to zero in on a value perhaps similar to 4.666, etc., etc., etc. So approximately 4.67 as you round it. Okay, and so that would be, and that could be verified if we were to use even higher number of subintervals, rectangular strips, to find the area under the curve. Okay, so that's how we would go about finding the area under a curve of a function that we know the equation for. So this brings us to the definition of the definite interval. So suppose we say that we have some sort of function, and the function is increasing on some interval. Say the interval is a less than or equal to some value of x less than or equal to b. Okay, so the function is increasing, some sort of thing like that perhaps. We know it's increasing, it's positive, and we divide, again, we divide it up into rectangles, rectangular strips, all the way along, and the width of which, if this is a and this is b here, if we take this distance, that distance between the two is distance b minus a, and if we divide that distance b minus a by all the number of strips we have, suppose there are n strips, then each one of those strips, each width, is going to be b minus a divided by n. So we're going to say that width is b minus a divided by n. Okay? And so suppose we have all these different iterations, and as my props go flying everywhere. So we have these, the rectangular strips. These are the lower rectangles, so we'd be finding a sub L over here. These are the upper rectangles. We'd be finding a sub U over here. So if we take find the area of a sub u, so the area of all the upper rectangles, then what we're going to have is we're going to have the width, and we're going to multiply that. Now remember, we're doing rectangles. We're multiplying by f of, well, this is a, which we're going to call x naught. Then the next x value will be x1, the next value will be x2, etc., all the way up to x sub n, which is b. So the x value before that would be x sub n minus 1, so it's 1 x value less than n. And this is x sub n minus 2, which is 2x values less than n. So for the upper rectangles, we've got the width, which is just going to leave as w for now, the width multiplied by f of x1, and then we're going to go to, we add the second rectangle, which is width multiplied by f of x2, because we're talking about this, the x value that leads the or forms the rectangle where the upper right corner of the rectangle is on the curve, on the function. Then we've got plus w f of x3, etc., 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 and then we continue along with that, and we can include these other ones here. So we've got w times f of x n minus 2, and then so that's this rectangle that is not shown here is this rectangle that's over here, because that's the x value leading to the upper right corner, plus w f of x n minus 1 plus w f of x n, x sub n. Okay, so we add all those things together, and that can actually be simplified to, so if we were to factor out all these w's, we factor out the w, and then we use summation notation. This is we use the index I equals 1 to n of f of x sub I. Okay, again, it's the whole thing is the sum of all these rectangular areas added together, and this is how we can summarize that.